Have you ever stopped to think about what really happens when you save a file or download a picture? I mean, we click, drag, and drop files all day long, but underneath that super simple action is this entire hidden world, this incredibly complex system that's running the show. So today, we're going to dive in and uncover the secret life of files. We're going to explore the file system, the invisible engine that organizes our whole digital life. So here's our game plan. We'll start with the absolute basics. What even is a file to a computer? Then, we'll look at how the system juggles millions of them without breaking a sweat. After that, we'll get into how it physically places all that data onto a disk, what the master plan is that coordinates everything, and finally, how it keeps all your important stuff safe and sound.
All right, first up, what exactly is a file? I mean, to us, it's just an icon on the screen, right? Something we click on. But to the operating system, oh, it's a completely different universe. So let's start with a really simple question. You're in a document, you hit save, and that's it. But what are you really telling the computer to do? You're not just throwing random data into the void. You're actually creating a very specific, structured entry in what is basically a massive digital library.
See, to your operating system, a file isn't a quarterly report or that great photo from vacation. Nope. To the computer, it's just a sequence of bytes, a stream of ones and zeros. So I want you to think of your hard drive as a giant library, and every single file is a book. The actual words in the book are the bytes, but the system needs a way to find that book and figure out what it's all about.
And that's where something called metadata comes in. This is, for all intents and purposes, a library card for every single file. It's got the obvious stuff, the name, that's the book's title, and its size, kind of like the number of pages. But it also tracks the file type, like its genre, its exact location on the disk, which shelf it's on, who's allowed to read it, and even timestamps for when it was created or last modified. Without this library card, the file would be completely and utterly lost.
Okay, so we've got our books, and each book has a neat little library card. That's great. But what happens when your library has millions, maybe even billions of books? You're going to need a seriously good system to organize the whole place. Because without that organization, you just have absolute chaos. Seriously, picture walking into a library where every single book is just thrown into one giant pile on the floor. How would you ever find anything? It'd be impossible. Well, that is exactly what a hard drive would look like without a directory structure. The solution to this mess is the directory, or, what we all just call a folder. In our library analogy, this is the master card catalog. It doesn't hold the books themselves, but it holds all that crucial information from the library cards, telling the system precisely where to go to find every single book. Now, this system didn't just appear out of thin air. Early computers had just one giant catalog for the entire library, a total mess if you had more than one person using it. Then they got a little smarter and created separate catalogs for each user, definitely an improvement. But the real game changer was the tree-structured directory, catalogs inside of catalogs. That's right, the folders within folders system we all use today. It's what allows for such deep and logical organization. Okay, so we've got our card catalog all nice and organized, but that only tells us where to find the book. Now we have to figure out how to physically arrange the books themselves on the shelves, and this is where the system gets really, really clever. So, this is the big question, right? How does the system take a file, our book, with all of its pages or data blocks, and actually arrange them on the shelves of the hard drive? Well, as it turns out, there's more than one way to do it. The operating system basically has three main strategies for this, and each one is a fascinating puzzle of trade-offs. You're constantly balancing speed, flexibility, and how efficiently you use space. And believe me, no single strategy is perfect for every single situation. This table lays it all out beautifully. First up, we've got contiguous allocation. It's simple. Put all the pieces of the file right next to each other in one continuous block. Super fast to read. But the catch? If your file needs to get bigger and there's no empty space next to it, you're out of luck. Next is linked. Here, each piece just has a pointer to where the next one is, kind of like a scavenger hunt. This is incredibly flexible. The pieces can be scattered all over the disk. The downside? It can be slow to follow that chain. And if just one of those links breaks, you've lost the rest of the file. And finally, we have indexed. This is kind of the best of both worlds. One special index block acts like a table of contents, with pointers to all the other blocks. It's fast, it's flexible, and the only real drawback is the tiny bit of space that index block itself uses up. So who manages all of this? The card catalog, the shelving strategies. Who is the head librarian running this entire operation? Well, that would be the files system itself.
So when your application wants a file, it doesn't just go and grab it. The request travels down a pretty strict chain of command. First, the logical file system looks at the metadata, our library card, and the directory structure to figure out the basics. Once it knows what you want, the basic file system figures out which physical blocks on the disk it needs to get. And finally, the I/O control layer translates all of that into the specific, low-level commands the physical hardware can actually understand. It's a really beautiful and efficient way to delegate tasks. Now, to manage all this, our librarian keeps its own set of master maps right there on the disk. The boot control block is like the instruction manual for how to open the library up in the morning, how to boot the OS. The volume control block is like the daily ledger, keeping track of vital stats like how many shelves are full or empty, and of course, the directory structure is the master map to the entire library collection. All right, onto our final, and you could argue, most important topic, security and protection. I mean, our library can't just be a free-for-all. We can't have people just wandering in, checking out whatever they want, or worse, scribbling in the books. We need some roles. And the guiding philosophy for all of this is something called the principle of least privilege. It's a really simple but incredibly powerful idea. A user or a program should only be given the absolute bare minimum permissions it needs to do its job, and nothing more. Think about it. Your text editor needs to read and write your text files, sure, but does it need permission to delete critical system files? Absolutely not. This one principle prevents countless accidents and is a huge barrier against malicious software. So how does the system actually enforce this? It uses a concept called an access matrix, which is basically this big grid you see here. It's pretty simple. The rows represent who is asking, like user A or user B. The columns represent what they want to access, like File 1 or the printer. The checkmarks, or lack thereof, define the permissions. So if you follow the row for user A, you can see they can read and write to File 1. But if you go all the way over to the printer column, access denied. It's a crystal clear, unambiguous way to map out every single permission in the entire system. And this slide does a brilliant job of showing the two main ways systems put that matrix into practice. The first is an access control list, or ACL. This is a list that's attached to the file itself. It's like a bouncer's list at a nightclub door saying, here's who's allowed in. The other way is with the capability list. This is the reverse. It's held by the user, and it's more like a set of keys or tickets. It says, here are all the doors that I'm allowed to open. Both get you to the same place, just by looking at the problem from two different angles. So, there you have it. We went all the way from a simple click on an icon deep down into the complex machinery of organization, allocation, and protection. It's this incredible invisible dance between logic and hardware that makes our entire digital world even possible. So the next time you save a document or even just drag a file from one folder to another, just pause for a second. It's not just one simple action. It's a whole symphony of hidden operations, a silent, powerful, and elegant system working in the background to keep your entire digital library perfectly in order. What kind of hidden magic will you imagine happening behind the screen?